Okay, on this slide, we're going to spend a little bit of time talking about one specific molecule that's really important for biology, and that is water. So we can see up here, let me get this going. Here is our molecular formula for water, H2O. And when you draw water out to show how the atoms are interacting, this is what you get. We have our oxygen atom right here, and oxygen has a total of 8 of its own electrons. It has 2 in the first shell, and then 1, 2, 3, 4, 5, 6 in the next shell. And then we have hydrogen, but so oxygen on its own does not have a full outer shell. It's got 6 valence electrons. It's looking for 2 more. And so it can make covalent bonds with 2 separate hydrogen atoms. So we have one hydrogen atom here. Here's the nucleus, which is basically 1 proton. And this hydrogen atom has 1 outer shell electron right here. And here's another hydrogen down here. And this is its outer shell electron. And if these atoms get close enough to each other, they can end up merging their outer shells and sharing. So here we have a shared pair. This electron here is coming from the oxygen, and this green one here is coming from the hydrogen. So this is a shared pair of electrons between these 2 atoms, and that basically makes a covalent bond. So we could draw a straight line here to show that this hydrogen here is attached to this oxygen here by a covalent bond. And the same thing's happening here. There's a shared pair of electrons right here. Here's one of them, and here's the other one. And so this is a shared pair. We can draw a line like this. So while the actual sort of Bohr diagram looks like this, we could draw a structural formula, and it's going to look like this. Oxygen, hydrogen with a covalent bond here, and hydrogen with a covalent bond here. So one molecule of water looks a lot like this. Now, there's something extra special or different or that goes on in water molecules that is very important to understand. And that is that we've got this covalent bond right here that's between the oxygen and the hydrogen. But oxygen is a much bigger atom than hydrogen, and oxygen actually has a great desire for electrons. And so we have an oxygen atom and a hydrogen atom. They're sharing a pair of electrons between them to make this covalent bond. But the oxygen doesn't like to share the electrons very fairly. It's like the big bully in the sandbox. The electrons are trying to go around the hydrogen and then around the oxygen, then around the hydrogen, around the oxygen, and evenly spread themselves between those 2 atoms. But the oxygen's like, no, I like them more. I really want to have the electrons in my outer shell. So it kind of sucks the electrons towards itself. And so while the electrons are supposed to be orbiting both the atoms, they spend most of their time sucked towards the oxygen atom. And the same thing is happening at this shared pair down here. This is another shared pair of electrons between this H and this O. But once again, the O has this great desire for electrons. It's bigger, it's more powerful. We say, there's a word for this desire or suckage of electrons. We say that oxygen is extremely electronegative. Electronegative. And the more electronegative an atom is, that's a measurement of how desperately the atom wants electrons and doesn't want to share them. It wants to suck them to itself and have them for itself. So sometimes I like to draw like little arrows on the covalent bonds here to show, look, that the electrons are being sucked up towards the oxygen. And the oxygen ends up with the electrons spending most of their time around it and not around the hydrogen atoms. Now, you can see it again in this diagram over here, on this diagram right down here. those big blue arrows show the kind of suckage of electrons away from the hydrogen towards the oxygen. And because electrons have a negative charge, and because the electrons are all being sucked towards the oxygen, you end up with more electrons by the oxygen part of the molecule. So, let me erase all this junk. So if the electron cloud is kind of whizzing around this molecule here, but the electrons go around the hydrogen, but then they go around the oxygen. They spend most of their time around the oxygen. Then eventually they escape and they go around the hydrogen, but then they get sucked back over here. And then they go around here, and then they get sucked back over here. And you can see that most of the time from my scribbles, the electrons are hanging out over by the oxygen. And since they're negatively charged, we end up with more negatives on this side of the molecule. And so we can say this side is partially, that's what this squiggle means, this S with a closed-in bottom, that means partially negative. And because the electrons are being sucked away from the hydrogen side of the molecule, the hydrogen side becomes partially positive. So from the left side to the right side of this water molecule, the side where the hydrogens are is a little bit positive, and the side where the oxygen is a little bit negative. It's not a complete charge, so it's not correct to say, I've lost my pen here, hold on. So what's not correct is for me to say that this is negative and this is positive. If that was true, then we'd say a whole electron has been moved over and gone forever from the hydrogen, but that's not true. It's just not being shared very fairly. It does go back to the hydrogens from time to time, but that's not all the time. So we say this is partially negative because the electron cloud is there mostly, and we say this is partially positive. And these partial charges, this is what we call them, partial, that means not complete, but partial charges are really, really important in biology and really important to water and some of the cool stuff that water can do.